Welcome to a new unit. Now we are ready to start talking about bonding, specifically ionic and covalent, and in this video we're going to be looking at ionic bonding. Are you ready to get started? Let's go. Alright, so the first thing with any kind of bonding is generally we're going to have to follow the octet rule. And the octet rule says that elements tend to gain or lose or share electrons in order to acquire a full octet. What is an octet, you may say? Well, in the first energy level, that's hydrogen and helium, a full octet consists of only 2 electrons. Hydrogen and helium for a full energy level only need 2 electrons. Pretty much everything else, the 2nd through 6th energy level, a full octet consists of 8 electrons. That's what you're normally thinking about when you think of octets. Incomplete and expanded octets do exist, so that an element might have 6 electrons or 12 electrons, but that's going to be discussed in more detail much later on when we start talking about Lewis structures. Right, so ionic bonding. Ionic bonding is a type of chemical bond formed through an electrostatic attraction, think Coulomb's law. Sometimes it's called a Coulombic attraction, between 2 oppositely charged ions, hence the name ionic bonding. So within ionic bonding, elements lose or gain, no sharing happening here, electrons in order to acquire the electronic configuration of the noble gases, formed from the transfer of electrons. They are losing and gaining, not sharing. They're formed between a cation, that's the positive ion, which is usually a metal, and an anion, that's the negative ion, which is usually a nonmetal. That's opposite sides of the periodic table, which have a very large difference in electronegativity. So generally, the very largest difference, say, between CS and F, the largest difference you can have is 3.1. And all types of bonding kind of fall on a continuum. So 1.9 is the cutoff, but it's really a gray area. Some say 1.7 is your cutoff. So a bond is more ionic the larger the difference in electronegativity is. So again, the larger the difference in electronegativity between the 2 atoms, the more ionic the bond. So a smaller electronegativity difference means it's more covalent. So within ionic bonding, you should already know this from the unit we've just finished, but isoelectronic are atoms that have the same number of electrons and therefore the same electronic configuration, such as argon, which has 18 electrons. An element that might be isoelectronic with argon is bromine minus, Br minus ion, because bromine has 17 electrons, but when you get that negative charge, it's gaining 1, so that has 18 electrons. Something else that might be isoelectronic is selenium, 2 minus. That's selenium that's gained 2 electrons, so that it has 18 electrons. Something else that might be isoelectronic with argon would be potassium. Specifically potassium plus, because potassium plus means it's lost an electron. It had 19, so now it's got 18 electrons. Or calcium. After it has lost 2 electrons, calcium 2 plus, it did have 20, but now it has 18 electrons. All of these things are isoelectronic with each other. They all have the same electronic configuration, which happens to be the configuration of the noble gas argon. For electronic configuration for ions, now we have already discussed this, but this is just a refresher. You should have the same configuration as the noble gas that it becomes isoelectronic with. The exceptions are some cations that have electrons in the D sublevel. We're going to get to that in a second. So before, the regular electronic configuration for sodium, Na, is Ne3S1. So when sodium loses an electron so that it can be Na+, it's going to lose this electron. So after it's lost an electron, it becomes Ne. But you can't write Ne for Ne. So really it's 1s2, 2s2, 2p6, because that is the configuration for Ne. And let's do F. Normal fluorine, 1s2, 2s2, 2p5. That's in its ground state. But when fluorine gains an electron so that it can become fluorine minus, then we're going to add 1 to what we had before, 1s2, 2s2, 2p6 instead of 2p5. All right, so try the calcium on your own. Hopefully you did that. Let's look at calcium. Normal calcium is argon 4s2. But now we have calcium plus 2, which means it's losing 2 electrons, and it's going to lose these 2 electrons, so it's going to become argon. But you can't write argon for argon, so instead the configuration of argon is neon 3s2 3p6. Alright, so here's a negative ion for you to try on your own. Try it on your own right now. Hit pause. Alright, hopefully you did that. Let's look at selenium. Typical selenium is argon 4s2 3d10 4p4. But selenium minus 2 means it's going to gain 2 electrons. It's going to gain them to that valence, the outermost energy level, so that it will become the same thing it was before, except now it's 4p6 instead of 4p4. Alright, so let's look at nickel. This is one of these exceptions. Typical nickel is argon 4s2 3d8. That is typical nickel. But nickel plus 2, so that it's going to gain lose 2 electrons, is going to lose 2 valence electrons from the highest energy level. 4 is a higher energy level than 3. So the highest energy level is the 4s2. That's what's going to go away. So nickel plus 2, after it's lost 2, will become argon 3d8. One more like that. Gallium is argon 4s2 3d10 4p1. Argon is going to lose, gallium is going to lose 3 electrons. So we're going to lose them from the highest energy level, that's the 4th energy level, and 3 of them. There's 1, 2, 3. So that's going to go away, that's going to go away. We will be left with Ar3d10. And in this case, both of these two guys do not become isoelectronic with a noble gas, because although they have the configuration of the noble gas, they also have d electrons. So just be aware of that. Right. Last thing we're going to talk about here for ionic compounds is Lewis structures. Now, Lewis structures, the reason Lewis is capitalized is that's named for Gilbert Lewis. These are structures that show where the electrons are in a molecule. And so for ionic molecules, or ionic compounds, it will show atoms with either 8 valence electrons or none, and no lines between them to show transfer of electrons. We're going to include full charges on the individual atoms because they are completely losing and gaining electrons. So for example, Na is in group 1. It should have 1 valence electron. Cl is in group 17. It should have 7 valence electrons. Well, sodium really wants to lose 1. Chlorine really wants to gain 1. So the 1 electron from sodium is going to transfer to the chlorine, so that sodium will now have none, and chlorine will now have 8. But when sodium lost its 1 electron, it became sodium positive, and when chlorine gained an electron, it became Cl negative. So now we see the Coulombic attractions between the positive ion and the negative ion. That's what keeps the ionic compound together. The positive and negative charges attract, opposites attract. So we have essentially Na plus, Cl minus, ... And those two atoms are not connected at all. All right, let's do another one. MgBr2. Mg has 2 valence electrons. I'm putting them together because they're both the S's, and the S's would like to pair. And then Br, those each have 7. So hopefully you notice that magnesium being a metal, is going to want to lose electrons, in this case 2 because it has 2. One of them is going to go to one bromine, and the other one's going to go to the other bromine. So if magnesium is going to lose one electron to one bromine and one electron to the other bromine, the magnesium is going to be in between the two bromines. All right, so now the bromines, they had 7, now they will have 8 because they've each gained 1 from the magnesium. And so, since it had 7 and now it has 8, the bromine has a negative overall charge. The magnesium, since it lost 2, will have a +2 overall charge. All right, try CaO on your own. Pause the video now and try it by yourself. Hopefully you did that. We looked at calcium. It has 2 valence electrons. Oxygen has 6. I always put the first 2 together to represent the 2 S's, and the rest of them I separate until I have to pair them. That gives me an idea of that orbital filling diagram, so I know whether we've got paired electrons or unpaired electrons. So in this ionic compound, calcium's going to lose 2, both of them to the oxygen. So oxygen is going to gain 2, both of them from the calcium, which leaves me with calcium +2, oxygen -2, with dots. 8 dots around it to show the 8 valence electrons in the oxygen, no dots on calcium to show that calcium lost. That does not mean that calcium doesn't have any electrons. It actually has a full outer energy level. We just don't draw any there to show that it has lost its electrons to oxygen. Okay, that's all you need to know for ionic molecules. Join me next time for covalent.